To preface what we're going to talk about here with pattern recognition, I will tell you that when we use trigonometric substitution, we're going to use one of three trigonometric functions. We're either going to be using the secant of theta, the tangent of theta, or the sine of theta. And what I'm after right now is telling you how you know which one of these three we're going to be using. If our integral contains a square root of the form x squared plus a squared, then I'm going to be using the tangent function. I'll show you how this works with the right triangle. If we set up a right triangle with an acute angle theta, then what I want to do is I know that using Pythagorean theorem, x squared plus a squared can be related to a hypotenuse. And so I will identify the hypotenuse to be x squared plus a squared. That leaves the legs to be x or a. Knowing that I'm going to use a tangent function, and it's really incredibly useful to know that we're only going to be using the secant, the tangent, or the sine. With a plus in the radicand, I'm going to be using the tangent. So knowing I'm going to be using the tangent function, I want to set up a tangent of theta in such a way that I do not end up with a variable in a denominator. That means that the vertical side is going to be x and the horizontal side is going to be a. We then have that the tangent of theta is equal to x over a, which means that x is equal to a times the tangent of theta. That is the actual substitution that we're going to use. It will follow that the square root of x squared plus a squared is equal to a times the secant of theta. And at this point, I'm going to say something that I often say. When it comes to trig and calculus, the secant and the tangent often go together. If you think about their derivatives, they show up in each other's derivatives. And here, when we set up this triangle using the tangent function, my substitution is x is equal to a times the tangent of theta, and the square root turns out to be related to the secant of theta. For a radicand of the form x squared minus a squared, so if we have the square root of x squared minus a squared, then I know I'm going to be using the secant of theta. Let's set up a triangle and see how that's going to work. If we consider the Pythagorean theorem, then, well, let's just look. A squared plus b squared equals c squared. We know that c is related to the hypotenuse. And if I solve for, say, b squared, then I have b squared is equal to c squared minus a squared. Folks, the point here is I have a difference, and the first term is the hypotenuse squared, right? Inside the square root here, I have x squared minus a squared. I have a difference. The first term must be the hypotenuse squared. So I'll identify x to be the hypotenuse. I know I'm going to be using the secant function, and I'll elaborate on that in just a little bit. But if I'm going to be using an x and an a and a secant of theta, then if x is the hypotenuse, a must be the horizontal side. Let's get rid of this Pythagorean theorem stuff over here. And then use the Pythagorean theorem to identify that the third leg of the triangle is going to be the square root of x squared minus a squared. Now, looking at this triangle, you can see that the way this is laid out with x being the hypotenuse, x has to be larger than a. If the square root is the square root of x squared minus a squared, if that's going to evaluate to a positive number, x has to be larger than a. That's how I know that x has to be a hypotenuse. With the triangle set up this way, we can see that the secant of theta is going to be x over a, which means that x is equal to the secant of, x is equal to a times the secant of theta. And that is the actual substitution that we're going to use. We can see, based on the triangle, that the square root of x squared minus a squared will then equal a times the tangent of theta, thereby reinforcing that the secant tends to go with the tangent. If we have a square root of the form square root of a squared minus x squared, then by the same rationale that we used to identify x as the hypotenuse in the previous discussion, I know that a has to be larger than x if a squared minus x squared is going to be positive. And so I know that a should be related to the hypotenuse. X has to be smaller than a. X must be one of the sides of the triangle. One of the legs, I should say, not the hypotenuse. With a radicand of this type, we're going to be using the sine function. Now let's set up this triangle so that we can see how it's going to work. Identifying an acute angle as theta, and knowing that A is the hypotenuse, I now need to identify one side to be x. I'm going to use the vertical side because that's the one that's opposite the angle that I've identified as theta. The third leg of this triangle will be the square root of a squared minus x squared, based on the Pythagorean theorem yet again. We know by looking at this triangle, the sine of theta will be x over a, and I've set that up in such a way that I do not have a variable in the denominator. Our actual substitution is x is equal to a times the sine of theta. Looking at the triangle again, we can see that the square root of a squared minus x squared is going to equal a times the cosine of theta. And I think it's worth pointing out that just as secant goes with tangent in Pythagorean identities and in derivatives, and when we set up these substitutions, sine goes with cosine. So there is kind of a rationale to all of this, even though it seems maybe a little bit like I'm making it up. If we go back to the idea that we're only going to be using the secant, tangent, and sine function, I think I can share with you what I think is the reason that that is the case. If we let x equal a times the tangent of theta and then take its derivative, we get a positive a secant squared of theta d theta. Likewise, if x is a times the secant of theta, when we take a derivative, we don't have a minus sign. And if x is equal to a times the sine of theta, again, taking a derivative to get dx in terms of d theta, I do not end up with a minus sign. These are the three trigonometric functions whose derivatives do not involve a minus sign. I think that's the motivation. Knowing that we're only going to be using a secant, a tangent, or a sine function, it falls to us to then identify what we see in the radicand. If it's x squared plus a squared, that'll be tangent. If the variable is coming first, so I have x squared minus a squared, that's going to be secant. If the variable is coming second, so that I have a squared minus x squared, that's going to be the sine function. If you set up your triangles this way every single time, then you stand a much better chance of successfully completing the problems that require this.